Okay, so let's just dive right in. Picture this. You've got a program, a pretty simple text analysis tool. And with a single one-line change to the code, it suddenly runs unbelievably faster. And I don't mean just a little bit faster. I'm talking about a full-on 30 times faster speed boost.
That's right, 30 times faster. I mean, that's the kind of performance jump that can take a script that runs for 3 hours and turn it into one that's done in just 5 minutes. And this isn't some kind of super complex, high-level optimization trick. This is about one of the most fundamental concepts in all of programming. So that's the big question, isn't it? How is that even possible? How can one tiny choice, just one single line of code, have such a massive, massive impact? Well, that's the mystery we're going to unravel today. And it all comes down to the incredible power of data structures. To really get what's happening under the hood, we're going to use a simple but really powerful metaphor to think about two core concepts: recipes and ingredients. I love this way of thinking about it. An algorithm, that's just your set of instructions. It's the step-by-step recipe you follow to get something done. But, a recipe needs something to work on. And that's where your data structures come in. They are the ingredients. They're all about how you organize your data so the recipe can actually use it. See, a data structure isn't just a container. It's not just a box you throw stuff into. It's a method. It's a specific way of organizing your data. And it's so important because it determines how that data gets stored, how you access it, and how you change it. The way you structure your data directly, and I mean directly, impacts how efficiently your recipe, your algorithm, is going to run. Okay, so let's go back to our 30x example. The program was trying to find specific words in a huge text file. The first version, the slow one, it used a list, or an array. Now, to find a word in a list, you have to check every single item, one by one, right from the very beginning. So the more words you have, the slower it gets. But the second version, the fast one, used a set, which is a type of hash table. Now, instead of that slow one-by-one search, it uses this really clever thing called a hash function to instantly jump to the exact location where a word should be. It's kind of like the difference between reading every single name in a phone book versus just flipping directly to the right page. It's a total game changer. So we can feel that one method is faster. But computer scientists, they need a more formal way to describe this difference. They need a way to measure not just speed, but efficiency and how well something scales. And for that, they use a tool called Big O notation. Now, here's the thing a lot of people get wrong about Big O. It doesn't actually measure speed in seconds or milliseconds. What it does is it tells you how the runtime is going to be affected as your data gets bigger and bigger. It's all about measuring the growth rate, which is absolutely crucial if you want to predict how your code's going to perform at scale. Let's just look at a few of the most common ones. You've got O1, or constant time. This is basically the holy grail. It takes the same amount of time no matter how much data you throw at it. Then there's ON, or linear time. This means if you double the data, you pretty much double the time. And then you have stuff like ON squared, or quadratic time. And let's just say that gets slow very, very fast. And this brings us right back to our original problem. That slow list search, that was O of N, linear time. The more words we added to our filter, the longer it took. But the set lookup, that was O of 1, constant time. It didn't matter if we had 2 words to check or 2 million, the lookup time was pretty much instantaneous. And that is the secret sauce behind that incredible 30x speed boost. Now, hearing all this, you might be thinking, okay, cool, so I should just use sets for everything, right? Well, not so fast. It's not quite that simple. The real lesson here is that it's all about choosing the right tool for the job, because every single data structure comes with its own set of trade-offs. For instance, an array is amazing for grabbing an item if you know its exact position, its index. A linked list is fantastic if you need to add or remove items really quickly. And our friend the hash table, well, it's super fast for lookups, but it can be kind of inefficient with how it uses memory. So the key takeaway is this. You have to pick the data structure whose advantages fit your specific problem and whose disadvantages you can live with. So all of this, the metaphors, the Big O notation, the trade-offs, it's all pointing to a timeless, fundamental truth about what a computer program really is at its heart. This famous equation from the legendary computer scientist Nicholas Wirth just says it all perfectly. At its absolute core, every single program you have ever used is just a collection of algorithms, the recipes, acting on a collection of data structures, the ingredients. That's it. That is the entire foundation.
And we can even extend that beautiful idea. If you want to go from writing code that just works to writing code that works brilliantly, you have to master both sides of that equation. You need excellent algorithms, and you have to combine them with efficient data structures. That's the real key to creating superior, high-performance programs.
Which brings us to one last thought. We live in this amazing age of AI assistants that can write tons of code for us. But do they always choose the most efficient data structure? Do they truly understand the subtle trade-offs? It makes you wonder, perhaps knowing these fundamentals isn't just some old school skill. Maybe it's more essential now than ever before, so we can guide these new tools to build truly incredible software. What do you think?